But we just showed this as a cycle. So that is equal to 0. So we do have the desired property that we have. Okay, so it says, then for the second stage, it's very similar to what we proved in 6.12. Do you want me to go through this, or should we move on? For x, regular space. No, I shouldn't say regular. Space. It's the same thing, so Tn of sigma is going to be...
And we can just sketch what the remainder of the proof is. He says, the remainder of the proof proceeds as in the second stage of the preceding lemma.
Mm-hmm.
Oh, so basically you have... What have you shown so far?
So we showed that we do have Tn that satisfies this property that we're looking for on a convex set.
Oh,
and so for a regular set, if we define it like this, Tn of sigma is equal to the induced map sigma of Tn delta n. Then it's going to be the same.
Extend that linearly and then...
I worked through it, so I think I worked through it. I think I worked through it well. I'll just do it really quick.
Okay.
So we have boundary Tn sigma is equal to boundary of sigma $, hashtag Tn.
Hey. Just warned you about that.
Oops. Okay, and then because sigma is a chain map, you can switch these. So it's very similar to the second part of that proof. Boundary of Tn. Okay. Right, and then by...
Let's start a hashtag. Hashtag, not a hashtag. And then...
Whoa, it's a paradox, guys. It's like saying, this is a lie.
Hashtag, not a hashtag. Boundary sigma, some number.
Right, okay. So, and we already know that boundary of Tn of, because this is, because delta n is the standard n simplex is convex, this is of, let's see, sigma minus st, not sigma, sorry, delta, minus st delta, and minus Tn minus 1 delta n is equal to sigma minus st sigma minus Tn minus 1 sigma. And so we have the desired result.
It's cool. So you're able to just sort of use the property of the induced map and the what you already know. So it really is, like you said, just like the second part of the
It's nice. It very easily follows. It says we use an exercise that the Tn's constitute the desired chain homotopy. That as a hint. I honestly didn't really think through this too much, so I apologize if you wanted to. If you wanted to try to work through it, we could, but I don't think so.
You can just, I think, a good thing to state here at the end would be corollary 6.14.
Right. Okay. Yeah, that's kind of. So we showed that it induces the identity. So 6.4 says that repeating SD also induces the identity. It's kind of straightforward, I think. If you
See, I'm looking at... See, this corollary, when I think about it, intuitively, it seems to me it's saying that the class of Z is the same class as the Qth subdivision of Z. So if you keep I guess that's repeated application of subdivision, right?
Yes.
It's like
So,
Q-fold subdivisions of Z. Just saying, not only does
you subdivide the subdivisions as well.
right,
so
you
you just keep getting like lots of little triangles, and so that's actually going to be very useful for proving excision.
chop. Although I think we tend to use it sort of the other way around. We start with sort of like this. I mean, analytically speaking, as I think about subdivisions which model, say, areas or volumes that I'm interested in from an integration perspective, I want to really, really fine subdivisions so my error is really small. But then, going backwards, the course's subdivision in some sense would be like topologically equivalent. I am speaking vagaries, but anyway, forgive me.
So now we're defining a fine n chain, which we had to find n simplexes. So it's basically going to be like the extension of that. So it's going to be a linear combination of a fine simplexes. If each sigma I is a fine. Okay. That's fine. Okay, then we have another definition. The mesh. So same, he subspace of an Euclidean space if gamma is equal to some mj sigma j, where all of them are different than 0. Then we define this mesh of gamma to be equal to the supremum over j of the diameter sigma j delta n. Okay, so it's really, like, to my understanding, so you guys remember where the diameter of a simplex is? It's the greatest possible distance between 2 points, which is just the greatest possible difference between two vertices. And so the mesh is just going to be the supremum of the boundaries that the gamma is made up of. Okay, and since
So the mesh is a number, huh?
yeah. So it says note that sigma j of the standard n simplex is compact because sigma j is continuous and delta n is compact.
Uh-huh.
That this has a finite diameter. Okay. And it says follows immediately from theorem 2.9 that E is a subspace of some. This is something I was thinking a bit about. We're getting close to being out of time. So.
Yeah, if you have to prove anything, you better stop.
Yeah. Well, it talks about like something following immediately. I like kind of try to work through it, but I'm not really sure.
Well, that seems like a good place to pick back up next
I'll
time.
think about it some more before we get.
So we have made it to theorem 6.15 by my count. Very good.
Alright, thanks guys.
Oh, yeah.